In this screencast, I will be discussing the math practicum and industry I did. The company that I did my practicum with was Parallel Design Incorporated. This company is a product development firm. They handle a lot of aspects of the production of products from the design and prototype phase to the mass production and warehousing and shipping phase. The company has manufacturing facilities throughout Asia, but it's headquartered in my hometown of Worcester, Ohio, which made it easy to do my practicum over the summer. The company focuses on product innovation, but they also do much more. On Parallel's website, they list all the different services they provide. The first one that comes up is website programming. They program for many different things that a company's website could need, as well as application-based code, such as coding, programming for machines that do certain tasks, such as packaging the pills that a hospital would use. The next service they offer is logistics planning of delivering and making products, as well as multiple solutions for sourcing them. Another is the prototyping of products. This is kind of what I dealt with, as some prototypes are made out of plastic and have to be screwed together, but I'll get into that later. They offer designing and prototyping of any new products a company wants to make. The second to last service on their website is the engineering of products. A company would need this once they have a product they want to produce, but need to refine it for mass production. This is the area where my practicum fell the most. They analyze products to figure out what could go wrong with them and how to fix those issues. The last service they offer is innovative industrial design. They look at products and how a company wants to change them to figure out how they can make those changes. This helps companies address what the product needs to do or change things that don't work. So what was my practicum? I looked at the joints where screws are put into plastic products. This requires a boss, which is a piece of product where there is more plastic for the screw to thread into, and it makes it harder to break the piece off. But even with the more reinforced plastic, the piece can still break, which is what I looked at specifically. The two ways the piece can break are either by pulling the screw out of the plastic and breaking all the threads in it, or breaking the boss off entirely, screw and all. Knowing the forces where the two types of compromises happen is how the designers figure out how small the boss can be. It all depends on the outer diameter of the boss. The more plastic that's there, the stronger it'll be. So as the size of the boss increases, it becomes less likely that the entire boss will break and more likely that the force will pull the screw out. To start out the practicum, my supervisor gave me a packet with general information about screw joints and how they can break. This had everything from thread-forming screws to sheet metal screws to application problems and how to find the forces that'll break them. This gave me a lot of information, but I still had to do a good amount of other research on the forces that break plastic products and everything involved. Once I figured out what the information in the packet was actually saying and understood the concepts, I was able to look more closely at the other parts of the packet that actually had the information I needed for what I was doing. The first part of the packet that applied to the specific situation I was looking at was this table and diagram. The packet overall had a lot of recommendations for how to go about making plastic screw bosses and the dimensions of everything involved. For the thread-forming screws I was looking at, they recommended that the diameter of the screw receiving hole in the boss be 80% of the diameter of the screw, including the threads. This makes it so the screw has enough plastic to bite into, but so that there is also enough room for the screw to go in without cracking the plastic anywhere. This gave me the inner boss diameter based on the screw size, as it should be 80%. From there, I went to the next part of the packet, which gave formulas for the shear and break forces based on the absolute forces. This was definitely the most useful part of the packet, as it gave the formulas and the characteristic values of a bunch of different plastics, which will be used later. Since I was trying to compare the absolute forces needed to compromise the boss, I needed to solve the equations for absolute force. Doing this meant that the material characteristic values were inputs of the equations, which is shown in the formulas I derived in the spreadsheet I made. Moving into the products of the practicum, it's all based around these formulas. F equals Ks, which is the shear force, times pi, times the inner diameter of the boss times the length of the screw, is the equation for the force to shear the threads. The force to break the boss is pi over 4 times kz, which is the break force of the specific plastic they're looking at, times the outer diameter squared minus the inner diameter squared. So using these equations, I moved on to the final product of my practicum, which was the spreadsheet. Using the spreadsheet, a designer can input the necessary things and get back information about how small the boss can be to optimize performance and cost. So looking at the spreadsheet, we see that the required inputs are the screw type, which you simply select from a drop-down menu, This determines what the nominal screw diameter is, because that is just a size that comes from the screw size, as well as what the inner diameter of the boss should be, because that's based on the screw size. You also input the length of the screw and the two characteristic values of the specific plastic you're working with. Once all these are put in, we see that it generates a table with the absolute force needed for the two different compromise types, based on the outer diameter of the boss. The values highlighted in red are the forces required for the compromise that's going to happen. Which compromise happens depends on which one of the forces is less. So the one that requires less force is the one that's going to be highlighted. Where the highlighting switches is the smallest outer boss diameter that should be used, which makes a lot more sense if we look at it graphically. In the graph, we see that the shear force doesn't change depending on the boss's outer diameter. For this particular situation, it's about 220 newtons. So, once the outer diameter reaches a certain value, it can't be made any stronger by making it any bigger. The shear force is always going to be the same. But once the outer boss diameter drops below a certain amount, the force to break the boss becomes less. So that's what's going to happen. So this intersection point is the strongest the boss can get, because if the boss gets any bigger, the compromise that's going to happen is just the shear force, which stays the same no matter how big the boss gets. By finding the intersection of these two lines, a designer can figure out how small the outer boss diameter can be for the certain situation in order to maximize the strength, and this helps them to minimize the cost. As we can see, we can change all of these different values. We can pick from this list of screws, which is the sheet metal screws that Parallel uses, and we can input different screw lengths, and it'll give us all the different outer boss diameters that should be used, and they can easily find how small the boss should be. So as mentioned, the benefits to the company is that they can find the outer boss diameter and the overall boss size that maximizes the strength of the boss while minimizing the cost. So moving into what I learned from the practicum, I was exposed to using math in a business setting. A business such as Parallel is concerned with designing products that work well and cost as little as possible. They want to find the best ratio between these two things, as with most businesses that have any kind of product. It isn't cost effective to test a bunch of models to figure this out, so they need to figure out mathematically and be able to justify it. As we see on Parallel's website, one of the services they offer is optimizing for functionality, quality, and cost while maintaining design intent. This means that they're trying to find that perfect ratio between quality of a product and what the company wants to make it. I also gained experiences from my practicum that apply to my life now and in the future. Right now, I can take the things I learned in my content classes and apply them to a setting such as this. I was exposed to design and money context, so there's a lot of concepts I can apply this to. I also learned a good amount about basic physics, which is a subject I've never taken, and learned a lot of new things about the program Excel. The biggest benefit I can see for my future career is being able to answer my students when they ask when they will actually use what they're learning. I can talk about this experience directly, or if I apply what I learn in my content classes to this context, as I mentioned earlier, then I can tell them about those things too. Working with both product design and money and cost has shown me a lot about how much math is used in the real world. I can also use this experience to come up with real-world problems to give my students. This will help to keep them from asking when they'll actually use this in real life, as they'll be using it in a real-life context. A possible problem I could give them is having them do a simpler version of what I did. I would give them the equations I found and have them consider just one type of plastic and screw size, so it's not as robust as what I've done. So the only variable they're working with is the outer diameter of the boss. I would ask them what the size of the boss should be to use the least amount of plastic. This has them reasoning about what the variables represent, creating equations, figuring out how to find where the equations are equal, and algebraically solving for a variable. In order to find the answer, they would have to think about it logically and see that the shear force is always the same, so the size of the boss should be wherever the break force becomes less than the shear force. And this has the students looking at all the different standards listed on the slide. To assess this, I would just see if the students can come up with a justifiable answer. If they do, then they understand solving equations to find a condition that works for two different equations. There are multiple different approaches students could take, but as long as they can justify their approach to an answer, then it would show that they understand.